Hello everyone, welcome to the second video for Edexcel Physics past paper solution. This is Unit 2 IAL Gen 2017. So let's start. Question number 12. The photograph shows a model car. A solar cell is used to produce hydrogen and oxygen from water by electrolysis. The car then uses stored chemical energy by combining the hydrogen and oxygen fuel cell to drive a motor. The solar cell is illuminated for 1 hour. The light energy incident on the cell in that time is 4590 joule. Calculate the radiation flux of the incident light. Okay, so we need to find the radiation flux. So radiation flux, I'm using the letter I to denote the radiation flux. So radiation flux is I is equal to power upon area. So you need area, which is given, area of the solar cell, but you need to figure out power, and power is energy upon time. So you can find first power and put power here and figure out in radiation flux. So first, if you calculate power is 4590, which is the energy per unit time. Time is 1 hour, and if you convert 1 hour into second, it is 3600 second. And if you divide these two, your power would be 1.275 watt. And then radiation flux I would be equal to power 1.275 divided by area. Area is 5 to the power minus 3. So you can put 0.005 or 10 to the power minus 3. It's fine. So radiation flux is around 255 watt per meter square or meter minus 2. So this is your radiation flux. Part 2, the hydrogen and oxygen gas produced in 1 hour stores 110 joule in chemical energy. Determine the efficiency of the arrangement transferring light energy to stored chemical. So we just need to find the efficiency, and efficiency E is output power divided by input. Or you can use output energy E out divided by input energy. So both are valid because energy is given. So I'm going to use energy formula, output energy over input energy. So in efficiency E is equal to output is 110 divided by input, and the previous part input energy was given as 4590 joule, and multiply by 100 because we need to find efficiency in percentage. So if you solve this, your answer would be 2.4%. So it's just 2.4% efficient. This is the efficiency. Explain why this arrangement is not viable in a full-sized car. Of course, you have seen in the previous part that efficiency is very low Moreover, it's take a long time to recharge, and just for a small amount of energy is is stored. So a long time required to recharge, and efficiency is quite low. And of course, you can put this arrangement works on the basis of the recharging is on the basis of solar cell, so it works only during daytime, not in the night. So that's how you can summarize. 13. Polarizing filter may be used to investigate a stress pattern in transparent material. Describe the difference between unpolarized and polarized light. It's a typical definition between unpolarized and polarized light. So unpolarized light is if this is the source, then source emit a light in many plane. That means we have a light in horizontal plane, or maybe a vertical plane. I'm sorry about my drawing, but you can imagine we have a vertical and horizontal and some 45-degree and 135. So we have a many plane in which light uh, can oscillate, or it's better if I draw like that. So it is vertical plane oscillation. This is horizontal plane oscillation. Maybe waves are coming horizontally, and in between vertical and horizontal in these angles. So you can imagine that these are wave oscillation in different plane, and you can imagine there are other planes of oscillation like this. So many plane. So an unpolarized light oscillates in many plane, while the polarized light only uh, oscillates in one plane. So when you pass this polarized unpolarized light through the filter, all the uh, oscillation which are not uh, parallel to the plane of polarizer, they are stopped, and only one oscillation is allowed, which is called polarized light. So that's how you write the definition, and this is a typical definition, generally comes in exam. So unpolarized light consists of many plane, and polarized light oscillate only in one plane, which include the direction of the propagation. So sometimes students get confused about this statement. What is the meaning of include the direction of propagation? So if you see, this is the light oscillating in many plane, horizontal, in between, and the vertical plane, and this is a polarizing filter which is a vertically aligned. So only vertical oscillation, which is this one, is allowed to pass. So this is polarized light. And if you see, the oscillation of the wave is in vertical plane, and the plane itself, this is the plane itself is moving horizontally. So the oscillation is in the same plane which is propagating. This is the meaning of include the direction of propagation. So I'm just explaining one more point, because I guess we need in some upcoming question. This sometime these types of question come in exam. So if you see, this is vertically aligned uh, polarizer. So this arrangement allows only one plane, while the other second filter is perpendicularly perpendicular to the oscillation. That means on the other side you don't see a light coming out. So if you rotate this second filter with a 90-degree, that means they have the same vertical line. So this polarized light also can pass through the second filter, but not in this case. A polarizing filter is placed above a source of unpolarized light. A second filter is placed over the first filter so that the filters are aligned as shown in the photograph. So these are two filters, aligned filters. That means their uh, grids or their polarizer are aligned. A second filter is then rotated by 90 degrees and the result is shown in the photograph. So explain the appearance of the photograph too. It's quite clear in the previous example I gave you. In photograph 1, because both filters are aligned, that means when the light passed through the first filter, so before passing through the first filter, the light was unpolarized. Passing through the first filter, light is polarized, and only one oscillation is coming out from the second filter. And as from the first filter. And as the second filter is aligned, so this polarized light is also coming out from the second filter. That's why we see the bright image. But as the second filter is rotated to the 90 degree, so the grids or the filter is not aligned and stop all the light that is coming out from the first filter. That's why we see the dark image. So the second filter is blocking all the light coming out from the first filter. That's how you explain it. A sheet of thin transparent plastic is stretched and then placed between the filters. The result is shown in photograph 3. Explain why the stretched plastic produce the pattern shown in the photograph 3. Now if you see and you compare the previous part, it was a completely dark because all the light coming out from the first is stopped by the second filter because of 90-degree alignment. But so what happened? A light comes from the first filter, which is polarized light, is transmitting through the plastic because it is a transparent medium, so it is transmitting from the plastic. But as the plastic is stretched, so some planes of light is rotated, and some of the rotated plane is parallel to the second filter that is coming out from the second filter. So these regions are the lights whose planes are rotated and then parallel to the second filter. They are coming out from the second one. That's why we see the bright image. So you can reframe your answer like that. Okay. Question number 14. An orange cell is made by inserting magnesium and copper electrodes into an orange. The orange cell acts as a source of EMF which can be used to power a clock as shown. So this is clock, orange. Okay. The following measurements are obtained from the circuit. EMF 1.79, PD 1.72, current 4.2 in a microampere. Show that the internal resistance of the orange cell is about 20 kilo ohm. You need to find internal resistance. That means small r, and EMF and voltage is given. So we have equation relating EMF and voltage. E is equal to V plus I R. So you can rearrange for internal resistance. R is E minus V divided by I. If you put all the numbers, E is 1.79, V is 1.72, I is 4.2, but don't forget it's not 4.2, it's 4.2 10 to the power minus 6. It is a micro ampere. Don't forget. So, okay, I'll just write 1.79. This is 1.79 minus 1.72 divided by 4.2 into 10 to the power minus 6. When you solve this, you have internal resistance around 0.0166 into 10 to the power minus 6 ohm. So you can shift this decimal on the right side. So you can say that, because you need to give answer in kilo mean 10 to the power 3, so you need to shift to make it uh, kilo. So you can rearrange, or you can shift the decimal and make it like 16700 ohm, and then you can write it around 16.7, so it's around 1700, 17, not 100, 17,000 ohm, and it's of course equal approximately 20 kilo ohm. So your answer is 17,000, or later on you can write R is about 20 kilo ohm. Part B, calculate the output power of the cell when it is used to power the clock. So calculating the power is again a straightforward question. Power P is equal to VI. So voltage is output voltage, which is 1.72. Current is 4.2 into 10 to the power minus 6. And you solve this, you have power is equal to 7.2 into 10 to the power minus 6 watt. Part C, the EMF measurement was obtained by removing a clock and connecting a voltmeter with a resistance of 1 to the power 7 ohm across the electrode. Discuss the suitability of this method. If you see in the previous question, part A, we calculate internal resistance R, which is around 17,000 ohm, and if you see the resistance of the voltmeter is 10 to the power 7 ohm, which is quite huge compared to the resistance. So you can say that the resistance of the voltmeter is much greater than the internal resistance. Moreover, in addition, you see the amount of current. It is current in a micro. So current is very small. Current is very small. So if you see the equation, E is equal to V plus IR, this IR can be considered as approximately 0. Why is that? Because R is very small, I is very small, so you can consider it as 0. So finally you will get E is equal to voltage. So voltage shown in the ohm meter will be equal to the EMF. So this is the suitable method to calculate the EMF. Question number 15. Excuse me. The photograph shows a Bluemorpho butterfly. The wings appear bright blue, but they do not contain blue pigment. The blue color is caused by superposition of light reflected from the scales on the wings. State what is meant by principle of superposition. So principle of superposition is, if two waves are coming, this is the wave 1 with the amplitude y1, and another wave is coming with the amplitude y2, and they both waves are interfering at some point. That means at this point the resultant wave resultant wave, we get the resultant wave, and the amplitude of the resultant wave is y. So the amplitude is the of the resultant y is sum of the individual amplitude. So during interference, amplitude of the resultant wave is sum of the amplitude of the resultant one, and the waves are, of course, the coherent waves that are coming out and meet at a point. So you can explain. The scales on the wings are a few micrometer in size and have a series of ridges from which light is reflected. You can see these are the ridges in the scale and shown here. White light reflects from the ridges X and Y. This causes a path difference between the light reflected from X and the light reflected from Y as the light reaches the observer as shown. So from two scales, this is point X, point Y. One first light reflecting from X, second is clearly we have a path difference. So the observer, we must have some interference pattern according to what the path difference is. So explain why some wavelength of the light will be observed strongly and other will not be observed. This is again a typical question of interference of light. Interference of light, or you can say a wave, interference of wave, or maybe interference of sound. And we used a similar answer for all such situation. In general, you can say that when two coherent light or two coherent waves or two coherent sounds interact at a point, then they interact constructively or destructively. So if the path difference is equal to n lambda, then we expect a constructive interference or a bright color or a high sound for path difference n lambda, and phase are and the waves are in phase. And if the path difference is n plus half of lambda, then we expect a destructive interference, and we expect no light or no wave or no sound at that condition. So that's how you incorporate all the points, and that's the reason. So the light coming from the ridges X and Y, if the path difference between these two light is equal to n lambda, then we observe a strong light, and some other point we do not observe because of the path difference of n plus half of lambda. That's how you can reframe all the situation. The table shows approximately wavelength ranges of the color of the spectrum. With the aid of calculation, show that the color observed would be blue for a butterfly where the distance d between x and y is 2.3 × 10⁻⁷ meter. So this is, sorry, okay, so this is the distance d, which is given 2.3 × 10⁻⁷. Now if you see, you need to figure out what should be the path difference. So ray which is coming at y is taking more distance. So in coming, this is d, and going out is d. So the total path difference difference is not D but 2D. Okay, so the idea is we need to figure out what the path difference is and then compare this path difference with the value given in the table. So meaning the path difference, in short I'm writing PD, path difference is 2 times of D, and D is 2.3 into 10 to the power minus 7 meter. If you multiply this, you will have answer 2 times 3 6, so 4.6 into 10 to the power minus 7 meter, and you can shift decimal towards right and you can write 460 into 10 to the power, this decimal decrease by 2 because I shifted 2 decimal place, so becomes minus 9 meter. These are some additional steps that I'm doing here just to make you understand. You can omit these 2 steps if you're okay with these. So 460 times power minus 9 meter, and you can rewrite 460 nanometer. Now see, the 460 nanometer lies 450 and between this region. This is the region of the 460. Okay, so you can say, you can write your comments that the 460 is a wavelength between 450 and 495. That's why the color is blue. So you can say that 460 is in between 450 and 495. That's why the color observed is blue. Thank you very much. That's it for this second video. See you in the next time. Have a nice time.